Somewhere deep inside a laboratory in Santa Barbara, California, a machine the size of a chandelier is doing something that should not be possible. It is not running faster than other computers. It is not storing more data. It is doing something far stranger. It is sending a signal into the fabric of reality itself and waiting for the universe to answer back. This is not science fiction. This is not a metaphor. This is Google's Willow quantum chip, and what it did in October of 2025 changed the way scientists think about computation, about information, and about the very nature of time. To understand what happened, you need to forget everything you know about computers. Forget the processor in your laptop. Forget the servers that run the internet. Forget even the most powerful supercomputers on Earth. Those massive warehouse-filling machines that can simulate weather patterns, model nuclear reactions, and crunch through astronomical datasets in seconds. Forget all of it. Because what Google built and what Willow demonstrated operates on a completely different set of rules. Not the rules of engineering, the rules of quantum physics. The story begins not in 2025, but decades earlier, when physicists first started asking a strange question. What if you could build a computer that didn't just process information as ones and zeros, but as something in between? A thing that existed in multiple states at once, that could explore every possible path through a problem simultaneously, and that would only reveal a definite answer when you actually looked at it? What if you could harness the weirdness of quantum mechanics? The same weirdness that makes atoms behave like waves, that allows particles to be in two places at once, that lets electrons tunnel through walls, and use it to compute? For most of the 20th century, this was a thought experiment. Brilliant, tantalizing, but utterly impractical. Quantum systems are extraordinarily fragile. The moment you interact with them, they collapse. The moment any heat, any vibration, any stray electromagnetic signal touches a quantum system, the delicate information it carries dissolves into noise. Scientists call this decoherence, and for decades, it was the wall that stopped quantum computing from becoming real. Google's Willow chip is the most serious assault on that wall that has ever been built. Willow is a superconducting quantum processor. It contains 105 qubits, the quantum equivalent of classical bits, except that each qubit can exist in a superposition of 0 and 1 simultaneously. That sounds like a simple upgrade. It is not. The power of quantum computing doesn't scale linearly, it scales exponentially. With each additional qubit, the computational space doubles. With 105 qubits, you are working in a space so vast that no classical computer could ever fully map it. But qubits alone are not enough. The critical challenge has always been error correction. Quantum systems make mistakes, constantly. Every operation, every gate, every measurement introduces a tiny probability of error. In classical computing, this is manageable. You can check your work, repeat operations, use redundancy. In quantum computing, checking your work destroys it. The act of measuring a quantum state collapses it. You cannot simply look at a qubit mid-computation and ask if it's still correct. For nearly 30 years, this was considered one of the fundamental barriers to useful quantum computing. You could build quantum systems, you could run short experiments, but the moment computations grew long and complex enough to actually be useful, errors would accumulate faster than you could catch them, and the whole thing would collapse into noise. In December of 2024, Google made a quiet but seismic announcement. Willow had crossed what researchers call the error correction threshold. As they added more qubits to the system, the error rate didn't go up as expected. It went down. This had never been demonstrated at scale before. It meant that Willow wasn't just a more powerful quantum chip. It was a self-improving one. The larger it grew, the more reliable it became. This single result invalidated 30 years of pessimism about whether fault-tolerant quantum computing was physically achievable. And then, in October of 2025, Willow did something even more remarkable. Something that required not just a better chip, but a completely new algorithm. An algorithm that did something scientists had never successfully done before on any quantum hardware. It sent a signal into a quantum system and listened for the echo. The algorithm is called quantum echoes. Its technical name involves a concept called out-of-time order correlators, or OTOCs, a phrase that already sounds like it belongs to a science fiction franchise, and which turns out to be even stranger than the name suggests. To understand what OTOCs measure and why they matter, you need to think about something called quantum chaos. In classical physics, chaos is familiar. A butterfly flaps its wings in Brazil, and through an unpredictable cascade of cause and effect, a storm forms over London 3 weeks later. The system is deterministic. Every event has a cause, but it is so sensitive to initial conditions that even tiny changes produce wildly different outcomes. This sensitivity makes chaotic systems nearly impossible to predict over long time scales. Quantum systems can be chaotic too, but in a far more profound way. In a quantum chaotic system, information doesn't just spread through space. It becomes scrambled through the quantum correlations between particles, a process called quantum scrambling. in a way that is so complete and so rapid that recovering any individual piece of information seems impossible. It's as if you took a message, translated it into quantum states, then shook those states through a system so complex that the message was scattered across millions of entangled particles simultaneously. Good luck finding it again. This is precisely what makes OTOCs so remarkable. They are a way of probing what happens to information as it gets scrambled through a quantum system, and here is the crucial insight: by running the scrambling process backwards. Imagine dropping a drop of ink into a glass of water. The ink spreads, it diffuses. Within seconds, the water is uniformly tinted, and the ink droplet is gone. Now imagine if you could reverse time inside that glass, run every water molecule backwards perfectly, and watch the ink reconverge into a single drop. The fact that it reconverges tells you something profound about the structure of the mixing process. If it doesn't reconverge, if even a tiny perturbation was introduced, the perfect reversal is broken and the echo fades. That is, in essence, what quantum echoes does. The Willow chip runs a complex quantum computation forward in time. It then introduces a tiny perturbation, disturbs a single qubit. Then it runs the computation backwards in time as precisely as it can. And it listens for the echo, the degree to which the original signal comes back. The strength of that echo and how it degrades with different perturbations tells you something fundamental about how the quantum system is processing and scrambling information. The reason this is hard is that running a quantum computation backwards is not simply pressing a reverse button. Every operation must be precisely inverted. Every entanglement must be unwound. The system must be held in coherence the entire time. And the echo signal, when it comes back, must be measured with enough precision to distinguish a genuine quantum result from the noise floor. For 65 of Willow's qubits, Google did exactly this, and what came back from the quantum system was a clean, verifiable signal that no classical computer could have produced. Here is why that word, verifiable, changes everything. In 2019, Google made a different kind of claim. Their Sycamore processor completed a specific computation in 200 seconds that they estimated would take the world's fastest supercomputer 10,000 years. The result was called quantum supremacy, and it generated enormous excitement and enormous controversy. Critics pointed out that the problem Sycamore solved had no practical value. It was essentially a carefully constructed benchmark designed to be hard for classical machines and easy for quantum ones. And when classical computing researchers worked at it, they found ways to simulate Sycamore's result far faster than Google's estimate. The 10,000-year claim shrank to days, then to hours, as algorithms improved. The milestone felt less like a breakthrough and more like a moving target. The quantum echo's result is different in a fundamental way. The output is not a random bit string, a sequence of ones and zeros that no one can check independently. The output is a quantum observable, a measurable physical value, like a current, a magnetization, or in this case, an OTOC value. These values are verifiable. If another quantum computer of similar quality runs the same experiment, it should produce the same answer. If a classical simulation tries to reproduce the result, you can check whether it's correct by comparing it to the quantum machine's output. The result is not a benchmark trick. It is a scientific measurement. Hartmut Neven, the founder and leader of Google Quantum AI, put it this way: this is the first time in history that any quantum computer has successfully run a verifiable algorithm that surpasses the ability of supercomputers. And crucially, Willow ran this algorithm 13,000 times faster than the best classical algorithm on one of the world's fastest supercomputers, the Frontier machine at Oak Ridge National Laboratory. Certain data points from the quantum echoes experiment would take Frontier over 3 years each to compute. Willow produced them in seconds. But Google went further than simply demonstrating a speed advantage. They applied quantum echoes to something real, something that begins to hint at the true promise of quantum computing as a practical tool. In collaboration with researchers at UC Berkeley, the team used the same quantum echoes technique as a kind of molecular ruler. They ran the algorithm on Willow to study the internal structure of 2 molecules, one with 15 atoms and another with 28. The results matched those from traditional nuclear magnetic resonance spectroscopy, while also revealing information about the molecules that NMR simply cannot access. This was not a benchmark. This was a quantum computer doing chemistry. The implications of that single result are staggering if you follow them to their conclusion. Nuclear magnetic resonance is one of the most powerful tools in drug discovery. It lets scientists probe the shape and dynamics of molecules, understand how proteins fold, identify how potential medicines bind to their targets. But NMR has fundamental limits. It cannot access certain quantum correlations in molecules that may be critically important for understanding biological processes. A quantum computer running quantum echoes can go where NMR cannot. In a world where developing a single new drug costs billions of dollars and takes over a decade, tools that can illuminate molecular structure with quantum precision are not academic luxuries. They are potentially transformative. The same logic applies to materials science. The battery in your phone, the superconductor in an MRI machine, the catalyst in an industrial chemical process, all of these involve quantum mechanical interactions at the atomic level that are too complex for classical computers to simulate accurately. The number of quantum states involved grows exponentially with the size of the system. For even a small molecule of practical interest, an exact classical simulation is simply impossible. But a quantum computer doesn't simulate quantum mechanics. It is quantum mechanics. It can explore those exponentially complex state spaces directly because it operates by the same rules. Google's quantum hardware team was at pains to point out the quality of the platform that made this possible. The current generation Willow chip, benefiting from continuous post-release improvements since its December 2024 launch, achieves fidelities of 99.97% for single qubit gates, 99.88% for entangling gates, and 99.5% for readout measurements. These numbers may seem abstract, but in quantum computing terms, they are extraordinary. Each percentage point of fidelity improvement represents an enormous engineering challenge. The operations run at speeds of tens to hundreds of nanoseconds. The qubits are cooled to temperatures close to absolute zero, colder than deep space, to suppress thermal noise. The control systems that manipulate these qubits must operate with a precision that would have been considered physically impossible 2 decades ago. The chip itself is manufactured by Google in Santa Barbara, California, the same facility where the company designs and tests all of its quantum hardware. This vertical integration matters. Unlike companies that rely on third-party fabrication, Google controls the entire stack from qubit design to algorithm development, using its open-source Circ framework to write and optimize quantum circuits. When something breaks, they fix it. When something can be improved, they improve it. The Willow chip that ran the Quantum Echoes experiment was a better machine than the one announced in December 2024, because Google had spent months refining it. Now consider what happened after the October 2025 announcement, because the story doesn't end in the laboratory. In December of 2025, the United Kingdom's National Quantum Computing Centre entered into a formal collaboration with Google Quantum AI, giving UK researchers direct access to the Willow processor. The UK Science Minister, Lord Patrick Vallance, framed the initiative as keeping British quantum innovators at the cutting edge. Target applications include drug discovery, materials science, and clean energy, 3 of the sectors most likely to be transformed by practical quantum computing in the coming decade. Researchers could submit proposals by January 2026, with successful applicants receiving processor access, research grants, and expert support from Google's quantum team. This partnership sits within a broader geopolitical context that is worth understanding. In September of 2025, US President Donald Trump and UK Prime Minister Keir Starmer signed what was called the UK-US Technology Prosperity Deal, which explicitly designated quantum computing as a strategic technology area and established a joint benchmarking task force. Quantum is no longer just a scientific discipline, it has become a matter of national strategy. The United States, China, the European Union, and the United Kingdom are all pouring resources into quantum research at a pace that recalls the space race of the 1960s. China has been particularly aggressive. The National Quantum Lab in Hefei unveiled a prototype quantum computing device small enough to be worn as a backpack, a publicity demonstration more than a practical tool, but one that signals the intensity of Chinese interest in portable quantum systems. Quantinuum, the quantum company headquartered jointly in Cambridge, England, and Colorado in the United States, reached a valuation of $10 billion in 2025. IBM continues to pursue its own superconducting qubit roadmap. Microsoft is betting on a different physical approach entirely, topological qubits, which would be inherently more stable than the transmon qubits Google uses, though they remain far less mature as a technology. Into this landscape, Google's Willow chip and the Quantum Echoes breakthrough arrive as a statement of intent. Not a final victory. Google's own team is emphatic about that, but the clearest sign yet of the direction of travel. What is the endgame? Where does this road lead? There are 2 milestones that quantum computing researchers talk about when they think about the technology's ultimate impact. The first is quantum advantage. When a quantum computer solves a practical, real-world problem faster or more accurately than any classical computer can. The Quantum Echoes result on molecular structure is arguably the first glimpse of this, though Google would be cautious about claiming it fully. The second milestone is far more consequential and far more distant, a cryptographically relevant quantum computer, capable of breaking the encryption algorithms that protect the internet, financial systems, military communications, and essentially all digital infrastructure. Breaking modern encryption requires a quantum computer of enormous scale. Not hundreds of qubits, but millions. Not just any qubits, but fault-tolerant logical qubits. with error rates orders of magnitude below what Willow currently achieves. The Willow chip, for all its extraordinary capabilities, is still what researchers call a nice-Q device, noisy intermediate-scale quantum. It represents the state of the art in that category. But the transition from nice-Q to fully fault-tolerant quantum computing is the mountain that remains to climb. Google's roadmap, which the company discusses openly, points toward larger and larger error-corrected systems, adding more qubits while continuing to improve fidelity, with an eye toward practical large-scale applications. Some analysts, looking at the trajectory of progress since 2019, have suggested that a cryptographically relevant quantum computer could arrive as early as 2029. This would be a profound geopolitical and security event, sometimes referred to in intelligence and cybersecurity circles as Q Day. The day when public key cryptography, which underpins most of the Internet's security infrastructure, becomes vulnerable. Governments and institutions are taking this timeline seriously. The U.S. National Institute of Standards and Technology finalized its first set of post-quantum cryptographic algorithms in 2024, encryption methods designed to resist attacks by quantum computers. The UK's National Cybersecurity Centre has been issuing guidance on post-quantum migration. The financial sector is beginning, slowly, to inventory its cryptographic assets and plan transitions. But here is the nuance that often gets lost in the alarm. The existence of a threat does not mean the threat is imminent or inevitable. Google's own team is clear that reaching a useful, cryptographically relevant quantum computer will require orders of magnitude improvements in system performance and scale, with millions of components yet to be developed and matured. The Willow chip is a proof of concept for the underlying physics, not a prototype of the device that would eventually threaten encryption. The road from Willow to that device is long, expensive, and technically uncertain. Yield to patient, meticulous work. The quantum echo's result is not just a computational milestone. It is evidence that the quantum computing enterprise is working as intended, that the theoretical predictions are matching experimental results, that the hardware is performing as the physicists said it would, and that the gap between laboratory demonstration and practical application is beginning, finally, to close. There is something philosophically remarkable about what the quantum echo's experiment actually measured. Out-of-time order correlators, OTOCs, are not just useful for probing molecules. They appear in some of the most fundamental equations in theoretical physics. They show up in the study of black holes, where physicists like Stephen Hawking and Juan Maldacena have debated for decades what happens to information when it falls past an event horizon. According to quantum mechanics, information cannot be destroyed. It must be preserved somewhere, somehow. But if it falls into a black hole, how does it ever come back? The answer, some theorists believe, involves exactly this kind of quantum scrambling that OTOCs measure. The information is scrambled across the black hole's horizon in a way so complex that recovering it is practically impossible, but theoretically, the echo is still there. Google's Willow chip, in a sense, is doing a tabletop experiment on the same mathematics that describes the information dynamics of black holes. The laboratory in Santa Barbara is, in a very specific and rigorous sense, probing the same equations that govern the most extreme environments in the universe, and somehow, improbably, the signal is answering back. That is the deepest meaning of what happened in October of 2025. It is not simply that Willow ran an algorithm faster than a supercomputer. It is not even that the result was verifiable, though that matters enormously. It is that a machine built by human hands, operating at temperatures colder than space, manipulating individual quantum particles with extraordinary precision, sent a signal into the quantum realm, ran it forward through chaos, disturbed it, reversed it perfectly, and received an echo that contained real information about the structure of the physical world. An echo that no classical machine could have heard. To truly appreciate the magnitude of what Willow accomplished, consider the competitive landscape it exists within. IBM has been building quantum computers for nearly a decade and has pursued an aggressive public roadmap, from 5 qubits in 2016 to over 1,000 qubits by 2023, but qubit count alone is a misleading metric, and IBM knows this. A system with 1,000 noisy, poorly connected qubits may be far less capable than a system with 100 high-fidelity, deeply interconnected ones. The race is not about raw qubit numbers. It is about quality, connectivity, coherence time, and error rates simultaneously. A 4-dimensional optimization problem that has no easy shortcuts. Microsoft has taken an entirely different bet. Rather than improving the same transmon superconducting qubits that Google uses, Microsoft has spent over a decade and billions of dollars pursuing topological qubits. A fundamentally different physical implementation that would, if it works, be inherently more resistant to errors. The physics of topological qubits is exotic even by quantum standards. involving quasi-particles called Majorana fermions that exist only in carefully engineered semiconductor nanowires. In 2025, Microsoft made progress in demonstrating the existence of topological gaps in these nanowires, but a fully functional topological qubit that outperforms conventional approaches remains elusive. If it ever arrives, it could leap past the NISQ era entirely. If it does not, the years spent pursuing it will have been an enormous detour. IonQ, another major player, uses a completely different physical substrate, trapped ion qubits. Individual atoms of ytterbium, suspended in electromagnetic fields and manipulated with lasers, serve as the quantum bits. Trapped ions naturally have extremely long coherence times. They hold their quantum states far longer than superconducting qubits, but they are slow to operate and difficult to scale to large numbers. IonQ's acquisition of Oxford Ionics in June 2025 for over $1 billion brought some of the most advanced trapped ion technology in the world under American ownership to the quiet concern of UK policymakers who watched one of Britain's most promising quantum hardware companies change hands. Quantinuum, the joint venture between Honeywell and Cambridge Quantum, also uses trapped ions and has made credible claims of high-fidelity quantum operations. Their valuation of $10 billion in 2025 reflects genuine investor confidence, not just hype, in their technical approach. They and Google are pursuing different paths up the same mountain, and it is genuinely unclear which path will prove more navigable at large scale. What makes Google's position distinctive is not just the Willow chip itself, but the ecosystem around it. The Cirq open source framework, the internal fabrication facility, the calibration teams, the algorithmic researchers, the partnerships with universities, and national labs. And now the growing early access program on Google Cloud. All of these form a flywheel that accelerates development in ways that no single breakthrough can fully capture. Google is not just building a better chip, it is building an industry. The history of computing has been a history of humans building tools to extend their ability to process information. The abacus, the difference engine, the vacuum tube, the transistor, the integrated circuit, the microprocessor. Each of these technologies extended the boundary of what humans could calculate, and each of them transformed the world in ways that the people who built them could only partially anticipate. Quantum computing is the next boundary, not because it is faster, though it is in certain domains incomprehensibly faster, but because it accesses a layer of reality that classical computing cannot reach. It computes in the same language that nature uses to describe atoms, molecules, materials, and possibly the structure of space-time itself. When you use a quantum computer to study a molecule, you are not building a model of the molecule. You are, in a profound sense, running the molecule. You are letting quantum mechanics compute quantum mechanics. The Willow chip is not the end of this story. It is, if anything, an early chapter. The engineers at Google's Quantum Lab are already thinking about what comes after Willow. Larger chips, better qubits, more sophisticated algorithms, new applications in chemistry, materials, medicine, finance, logistics, and fundamental physics. The roadmap extends well beyond the current hardware, and the lessons learned from Willow's error correction threshold in the quantum echoes experiment are already informing the design of what comes next. But in this moment, with the echoes of October 2025 still reverberating through the scientific community, it is worth pausing to appreciate what has been achieved. A quantum computer sent a signal through a chaotic system, reversed it in time, and listened for what came back. What came back was a verifiable answer, faster than any classical machine could find it, and true in a way that could be confirmed by another quantum computer of the same quality. For the first time, the quantum world did not just process information, it returned it, checked and confirmed in a form that science could use. The universe, it turns out, answers when you ask it the right question. Google's Willow chip just learned how to ask. And that is perhaps the most human thing about this entire story. For thousands of years, people have looked at the natural world and asked questions about the stars, about matter, about life, and found that the universe, when approached with sufficient rigor and care, does answer. It answers in the language of mathematics. It answers through experiment. It answers through pattern and structure and the slow accumulation of verified knowledge. Quantum computing is, at its deepest level, an extension of that ancient practice of questioning. It is a technology built not to impose our will on the world, but to listen more carefully to what the world is already saying. Every atom in existence is running quantum mechanics in real time, constantly, without effort or error. Quantum computers are tools that let us tap into that conversation, to ask nature questions in our own language, and receive answers that no translation into the binary world of classical computing could ever fully capture. The men and women who built Willow, who designed the quantum echoes algorithm, who cooled the chip to within a fraction of absolute zero, and then calibrated every qubit with obsessive precision, are part of a tradition that stretches from Archimedes to Newton to Einstein to Feynman. They are the people who believe that the universe has Structure, that the structure can be understood, and that understanding it is worth every year of effort, every failed experiment, every theoretical dead end, and every breakthrough that arrives not with a fanfare, but with a quiet measurement on a graph that shows unmistakably that the signal came back. It came back. Cleaner than expected, faster than any classical machine could have found it. Verifiable. Real. That is where we are in June of 2026, looking back at the autumn of 2025, and recognizing it perhaps as the moment the quantum age truly began. Not the moment quantum computing was invented. That was decades ago. Not even the moment it proved it could outperform classical machines. That was 2019. But the moment it proved it could be trusted. The moment its outputs became verifiable. The moment a quantum computer stopped being a curiosity and started being a scientific instrument. The Willow chip is not the end of the road. The challenges ahead, scaling to millions of fault-tolerant qubits, developing algorithms with real-world utility across medicine and chemistry and materials science, building the software tools that will let non-specialists harness quantum hardware. These are genuinely hard problems that will take years, perhaps decades, to solve fully. Nobody should expect Q-Day next year, or practical quantum drug discovery next month. Progress in fundamental technology is rarely as fast as the most optimistic voices predict. But it is also, history suggests, rarely as slow as the most cautious voices fear. The transistor was invented in 1947. The integrated circuit was demonstrated in 1958. The personal computer arrived in the mid-1970s. The internet became publicly accessible in the 1990s. At each stage, the people inside the technology could see the trajectory clearly while the world outside still thought it was science fiction. Today, the people inside quantum computing can see a trajectory. It is hard. It is uncertain. It is real. And somewhere in Santa Barbara, cool to a temperature colder than any star, a chip with 105 qubits is waiting for the next question. The universe, as it has always done, is ready to answer.